Okay? Glad you're in high spirits, but you need to be quiet and in high spirits, if you can manage that. Alright, I said in yesterday's tutorial that doing this course is rather like riding a very fast horse. At the moment we're out of the stable and we're kind of in a little trot. Okay, so it's just a trot. Okay, we're going to get... But just hold on tight, don't fall off at the trot. Okay, that's a bad place to fall off. In fact, don't fall off at all. But, yes. So I'll let you know... I'll let you know when we're going to speed up. Okay, all right. So, if you could please keep quiet. We've been talking about various kinds of surfaces. Okay, I was emphasizing it yesterday. I had said it in class, but I was also emphasizing it yesterday's tutorial. I'm giving you this week to become familiar with all of these surfaces that are in that table on page 17, 18. Okay, at the moment they might look a little bit strange to you, but come Monday, I expect you to know all these names, know what they look like, and be able to recognize which surface is which just by looking at its equation. Okay, you'll be able to recognize paraboloids, spheres, hyperbolic paraboloids, all of these various things. Hyperboloids of 1 and 2 sheets, that sort of thing. So, yeah, I'm going to frown at you if you can't do that come Monday. All right, hopefully today is the last day of having to rely on the built-in audio of the tablet because I'm going to see what I can do about sourcing a microphone this afternoon. Right, bounded solids. So we've been talking about surfaces, different kinds of surfaces. A very prominent role that surfaces play in this course is surfaces intersecting in order to make bounded solids. So you would say something like, we want to consider the region that's bounded by a cone at the bottom and a hemisphere at the top, or maybe an upside down paraboloid that's intersected by a plane, and you want to look at the region that's bounded by those surfaces. We're going to be doing a lot of integration in this course, a lot. We're going to be doing double integrals, surface integrals, triple integrals, and line integrals. And the double, triple, and surface integrals all relate to intersecting surfaces. And you need to know what the surfaces look like. You need to know how they intersect in order to figure out where the edges of your region edges, plural, of your region are, so that you can determine your limits of integration. It's those edges of your region that are going to give you your limits of integration. So you've got to be able to draw good pictures. You've got to be able to picture the stuff in your head. Okay, or do this with your hands in the air or whatever it is that helps you figure out what these things look like. Because if you muck up your limits of integration, well, you're lost. Okay, so just as a little bit of pre-practice before we get to the actual big chunky problems later on, let's do some drawing. So, just a little bit of writing and then I'll jump into an example. I'll basically write what I've just said. A prominent role of surfaces in the course is creating bounded solids. So basically three-dimensional regions, but we often call those three-dimensional regions solid. It's creating bounded solids by intersecting surfaces. Being able to draw such solids or regions. Oh, region starts with an R, not with an E. Is well, it's not just very important, it's absolutely vital. You'll not be a happy person if you can't do it. Very important. Okay, so let's just do some examples. I'll do a little bit and then you can do a little bit. Okay, I'm going to do 7A. Okay, so 7 says, sketch the solid in the first octant that is bounded by the graphs of the given equations. Now, the graph of the equation is the surface, okay? It's the picture of the surface. Okay, so sketch the solid that's bounded by the following. So let's have a look. In 7a, plus z squared equals 9, y equals 2x, y equals 0, and z equals 0. So we need to figure out what those look like so that we can draw. Now x equals 0, sorry, x is not one of them. Y equals 0 is the xz plane, and z equals 0 is the xy plane, the ground, as it were, the floor. Okay, so those are nice and easy. Those are what I call coordinate planes, okay, because they are the planes created by the coordinate axes. Okay, y equals 2x. What sort of surface is that? Now, if you're looking at that and thinking, that's not a surface, that's a line, well, you'd be right. In the xy plane, it is a line. But in three-dimensional space, it's a surface. It's a plane. You can see people doing sort of flat things with their hands. So. And then that top one, once again, you might be thinking, that's not a surface, that's a curve. And you'd be right, because in the xz plane, that's a circle. But in three-dimensional space, that's a surface, and it's a cylinder. It's a circular cylinder. Okay. Any curve on a coordinate plane. So, let me start again. Any equation that can be interpreted as a curve on one of the coordinate planes can also be interpreted as a surface in three-dimensional space. And you get that surface by taking that curve and pulling it out of its coordinate plane. So if you drew the line y equals 2x in the xy plane, okay, that would be, in three-dimensional space, that would be drawing a line on the ground, as it were. The xy plane is like the horizontal plane. Then you take that line and this is the way I describe it. Sorry, I'm kind of hunched because I want the mic to pick it up. I must look a bit funny. The terminology I use is you pull it out. So you take that curve, which is just a line, and you pull it out of the xy plane parallel to the z-axis. And as you do that, what you're forming is a sheet, like a vertical sheet, a plane. In the case of that circle, x squared plus z squared equals 9, that's a circle of radius 3 on the xz plane. So you take that circle and then you pull it out of the xz plane parallel to the y-axis, and it forms a circular cylinder. So any curve on a coordinate plane, any expression that describes a curve on a coordinate plane, also simultaneously describes a surface in 3D, and you get that surface by taking the curve and pulling it out parallel to the sort of other axis. So there was a hand up.
So the cylinder is centered around the y.
Correct, because it was centered on the origin on the xz plane, and so when you pull it out, it's now got the y-axis as its axis of symmetry, or as its center of rotation, or whatever you want to call it. Okay, alrighty then. So let's draw this thing. Okay, so the xz plane is that plane there that I've just labeled, and that's the y equals 0 plane. The z equals 0 plane is the xy plane. It's that horizontal base. Okay, so x squared plus z squared equals 9. I'm first going to draw it as a circle, but actually I'm only going to draw a quarter circle, because I know that I'm not actually interested in the rest. I'm only interested in that part because of the well, I suppose it's not exactly clear right now, but that's the only part I'm going to need. Now, I'm just going to draw dotted lines because I'm not going to keep them. Well, I'm not going to keep all of them. Left to its own devices, that curve would like to form a cylinder, or because I've only drawn a quarter of a curve, it's going to be a quarter of a cylinder. And it would just go on forever. But it's not being allowed to go on forever because we're bounding our region with these others. So we're bounding it with the way I've drawn it, the sort of left side is being chopped with the y equals 0 plane, and the bottom is being chopped with the z equals 0 plane. But there's another plane that's involved, and that's that y equals 2x plane. Now y equals 2x, if I draw it as a line on the xy plane, would look something like that on the xy plane. But of course, y equals 2x is not a line, it's a plane. It's a plane going vertically upward. So what's happening I'm left with that. Okay, so if I shade every surface, it will get a bit. Okay, those little vertical stripes I've drawn on the drawing are the plane at the back, the y equals 2x plane that's defining the back of my solid. Okay, I'm just going to pause the video because I'm going to move away, and then there'll just be this weird silence on the recording. Okay, so 7b was just that plane creating a tetrahedron. 7c, we start with our two xy curves, really, in the xy plane in order to find that lens-shaped cross-section. And then we think, okay, cool, so now we want a column going up, but that column going up is getting sliced. So you can almost think of that z equals x cubed surface as being almost like a blade, like a blade coming across and slicing through this column that would like to go up forever. So, again, let me do it in the classroom. Okay, let me pause. So what we have is a kind of a column that goes up. Come on, stylus. And down on that side, so it's like this. And I'm not a great drawer. Maybe this, maybe that would actually have a bit of a curve like that. I don't know. So it's got this lens-shaped cross-section, and it's almost got this sort of ski slope top as it's sliced by the cubic. Fun, huh? Yay! Surfaces, yay! Drawings, yay! Come on, you're engineers. Engineers love to draw. The more complicated the thing is, the more fun it is. Yes? You're right? Yes? I've seen the stuff you lot draw in drawing class. It's complicated. Question over there. I could, but it's not the convention. I use this exact convention for my axes every time. Let's have a look. If it were coming out of the page, what would it look like? Ooh, gosh, now you're taxing me here. Let's have a look. If Z were coming out, okay, all right. Yeah, okay, that would be like that. And then we'd have this lens like that. And then the cubic would be like so. So it would come out. Oh, it has to be parallel to the z-axis. Let me draw that a little bit differently. It'd come out like this and have some sort of cross-section over there. Okay, that's my little rough thingy. It's a column coming out of the xy plane parallel to the z-axis and being cut off with this cubic. I must admit, the curve of that cubic's not particularly clear. It should be curvy. It's being cut with this cubic. I really should change this question because I'm so bad at drawing it, but still, there we go. Okay, right, we have to move on. Coordinate systems. And so let's talk about coordinate systems. Right, 32 minutes past. No, hold on. What did you just do? You just jumped a page, didn't you? Do I want to jump a page? Sure, let's jump a page. Okay. In two-dimensional space in this course, we're going to flip between between rectangular coordinates and polar coordinates. In three-dimensional space in this course, we're going to flip between rectangular coordinates, cylindrical coordinates, and spherical coordinates. Some of the hardest questions that we can ask involve coordinate changes. So we're going to sometimes do a problem just exclusively in one coordinate system, and then we'll do other problems where you have to flip between coordinate systems. So you have to know how you describe points in space in these different coordinate systems, and also how you can change between them. And then ultimately what we'll be doing is integrals, where you have an integral that changes between coordinate systems, which is it's a little bit tricky. You've got to do it with a bit of finesse. So, coordinate systems. Let me look at my notes. Okay. If we use xy or xyz to describe a point in space, or to describe the position of a point in space, rectangular or a Cartesian is written with a capital C because it's named for a person. It's named for René Descartes, philosopher and mathematician. Okay, and of course we're very familiar with rectangular coordinates, and I imagine you're fairly familiar with polar coordinates as well in two-dimensional systems. Okay, so in 2D we can have a point over here, and we can describe it using its x and y coordinates by how far you have to move along the x-axis, and then how far you have to move parallel to the y-axis to get to that point. So it's almost like you start at the origin, how do you get to the dot, and you're giving somebody directions, and those directions go parallel to the coordinate axes. Okay, but there's another way of describing the exact same point. I suppose I should have done that dotted so it matched the other picture. Let me do that dotted. And you can describe that point by how far it is from the origin and what angle that dotted line makes with the positive x-axis. Always has to be with the positive x-axis. Yeah, actually, let me not even label the axes, because they needn't necessarily be x and y. They could be anything. Okay, so that's just a different way of describing where it is, and I imagine you've used polar in physics, surely, and in mathematics, the main place in first year where you would have seen that would have been in complex numbers, describing a point with its modulus and argument. Okay, so, but it's the same thing. Okay, that's not too tricky, and flipping between them isn't particularly hard. I think I've got some stuff in a box. Where's the box? Oh, I've focused on 3 dimensions in the box, so I'll come to that. Okay, in 3D, okay, and then we call this rectangular, and we call this polar. Okay, in 3D, if we have a point in space, we can describe it using its x, y, and z coordinates, and that would be rectangular, of course. Actually, let me not label the axis, it's just confusing if I'm using the same letter in a different sense. Okay, so you can label it, and that would be rectangular, and that's easy peasy. We know how to do that. Okay, and then there's cylindrical, and cylindrical is also not too bad, because in the 3D rectangular, it's exactly the same as the 2D rectangular. We've just added a z dimension. Same with cylindrical. Cylindrical is basically polar with a z dimension. So what you do is that same point. You can describe that point. So basically you take that point and you sort of let that point sort of cast a shadow down on the xy plane. You project the point down onto the xy plane. And then you describe where that projection is in terms of polar coordinates, r and theta. And then your point, you just add the z. So the r theta z. So it's really the same as polar, just with a sort of a height dimension, as it were. Okay, it's spherical, it gets a bit crazy. It isn't really, doesn't have a tight analogy to the others. So this is cylindrical. So spherical, that same point, sorry, I know I'm scrolling past that. I'll come back if you want me to. Spherical, that same point. Now we're no longer interested in the relationship between that point and, I suppose we are. So you do kind of project it down onto the xy plane, but you're not interested in z, and you're not interested in r, but you are interested in theta. So the only reason for projecting the point onto the xy plane is to get that theta. Rho is the distance between the point and the origin, and phi is the angle between the positive z-axis and the rho dotted line. Okay, so theta is the same old theta that we had in cylindrical and in polar. Rho is the distance to the origin, and phi is the angle between the positive z-axis and that dotted line that rho is measuring. Now, here is a little bit of a, yeah? X. So theta is always measured from the positive x-axis, just like we do in two-dimensional polar. So theta and phi are both interested in, they're both angles from a positive axis, one x, the other z. We never measure from y, interestingly enough. So there's a little bit of a clash here between different systems. I'm not really sure, it's probably deeply historical between different groups. But sometimes I don't even want to say, I don't even know where exactly, maybe certain branches of physics, I'm not really sure. But in some places you'll find phi actually measuring the complement of that, measuring from the xy plane upwards. So as you advance in your degree and you do various courses in engineering and maybe go on to do postgraduate engineering or whatever, you'll probably every now and again stumble across a coordinate system where phi is not that phi. It actually measures upward from the xy plane rather than outward from the z-axis. So if my phi was 30 degrees, then the phi in that other system would then be 60 degrees because it would be measuring the 90 degrees minus that. Okay, well, we're doing this. This is what we do in mathematics. This is what your textbook does. And this is what some branches of physics and engineering do. It's just there are others that don't. So I just want to let you know that. And throughout your career as an engineer, you need to be able to roll with symbols being used in different ways. For instance, in maths, we use I for complex numbers. But electrical engineers, or at least some of them, tend to use J. So what? You just learn to roll with that sort of thing. Okay, so that's spherical coordinates. So you're interested in phi as your coordinates. Okay, so here's one of my pet peeves. That is a rho. It is not a P. It's not the English letter P or the Latin letter P. It's the Greek letter rho. It makes a R sound. It doesn't make a P sound. Okay, it's a rho. You are going to do lots of very, very hard things in your life. You can manage to write a rho. And to say rho, not P. Okay, who's going to be the first person to call me over and say, I'm trying to find out P, and then I'll give you a smack. I won't actually give you a smack, but I'll think about it. It's rho, not P, and it doesn't have like a downstroke, like back in primary school when you were taught how to write your letters, and P's have a downstroke, and then you go up, and then it has a rho. It doesn't have that downstroke. Okay, so thank you for letting me get that out of my system. It's one of my pet peeves, people writing those as a P. Okay, so you need to be able to move. Let me just scroll up for anybody who's still wanting to look at what that cylindrical one looked like. You need to be able to translate between them. Given a point in certain coordinate system, changing it into a different one. And I've put everything that you need to know into that box on page 19 in the handbook. Okay? Okay, Yeah, I'll write it down here now, but it is all there. So I'm simply copying what's in the box. In 2 dimensions, the relationship between r and x is r is x squared plus y squared. Nice little Pythagoras going on there. Okay, rho squared for very similar Pythagorean reasons. Oh gosh, stylus, what you up to? Is x squared plus y squared plus z squared. So actually, interestingly enough, remember that problem 108 that I flipped forward to just now? Remember it had a density of 1 over x squared plus y squared plus z squared. And the region was described by hemispheres. I think, now in hindsight, that's probably a problem you would have solved in spherical coordinates, and instead of 1 over x squared plus y squared plus z squared, you would have had 1 over rho squared as the density. So you need to be able to flip between these and look at things and go, that would look so much nicer in spherical. Let me change. Okay, what else is there? In 2 dimensions, we can work out x from polar. Okay, and then here are the fun ones. Here are the fun ones. X in spherical coordinates is rho cos theta sine phi, and y is rho sine theta sine phi, and z is rho cos phi. And you've got to know those. Okay, you've got to know those. You've got to know those off by heart. I put them in a box on purpose. They're important. Okay? They take a little bit of memorizing, but there is a bit of a pattern, and that pattern helps. Notice how in 2 dimensions, x has a cos theta, and y has a sin theta. So it helps, that sort of cos theta, sin theta, sort of pattern re-emerging helps to remember them. And yeah, okay. Okay, so that stuff in the box there needs to be memorized. We just expect you to know it, and we expect you to recognize it. You run across a rho cos theta sine phi somewhere, you need to be able to look at it and go, oh, okay, in rectangular that would just be x. You just need to recognize it. So it's not that you can pull it out of your memory when called upon. You need to be able to look at it and go, oh, I recognize that. That's a familiar old friend.